Okay, so this is the acids and bases unit, and this is lesson 1. So acids and bases are a cornerstone of chemistry. These two substances have uses in industry, medicine, geology, cosmetics, and in the home as well. Ammonia, NH4OH, is a base that's used to clean grease, build up on floors. Hydrochloric acid, HCl, is used to partially dissolve the surface of concrete flooring so that it roughens to hold floor paint better. Hydrofluoric acid is used to etch glass. Meanwhile, sulfuric acid is used as a catalyst for certain reactions and as a reactant in refining iron ore. Sodium hydroxide, NaOH, is used in the production of soap when it combines with animal fat or vegetable oil. It's also used as drain cleaner. So what you'll learn is that acids have certain characteristics which are and include being very sour. They'll burn if you get them in your cuts. They have a pH less than 7. Bases, on the other hand, are usually very slippery feeling. All of your cleaners, your dish soap, your shampoo, your household cleaners for floors, those are all bases. They also taste very bitter, and they have a pH greater than 14. Svante Arrhenius was the first to describe the conductivity of electrolyte solutions and to hypothesize that solutions that conduct electricity contain dissolved ions. He also described acids and bases in terms of their properties. So we're going to talk about what makes an Arrhenius acid and base. Well, an Arrhenius acid has H plus as the only positive ion in solution. He also said that acids, especially strong acids, will dissociate in water. So here you have HCl plus H2O, and it forms H3O plus and Cl minus. The acid contains H plus, which combines with the H2O to form H3O. It's very easy to spot an Arrhenius acid because all acids start with H, as you can see here in HCl, in H2SO4, and in H3PO4. Another thing that we need to know about acids is that they eat away or oxidize active metals. So you're kind of familiar with table J already. You know that the most active metals are on top and the least active on the bottom. So any metal that is above H2 on table J will react with it in a single placement reaction. As you can see in the example here, lithium reacts with hydrochloric acid and hydrogen gas is produced, and lithium chloride, an aqueous solution, in its place. The same with calcium and hydrochloric acid. But if we were to choose a metal lower than hydrogen, copper, silver, or gold, then the reaction would not take place. As I said earlier, acids have a pH less than 7. What you need to know, though, is the closer you get to 1, the stronger the acid. Or the further you get from 7, which is neutral, the stronger the acid. Each pH value is a 10-fold increase in acid strength. Therefore, if I go from a pH of 5 to a pH of 3, that's 2 pH places, or 10 times 10, which is 100. So a pH of 3 is 100 times more acidic than a pH of 5. Acids conduct electricity, as I said, because you form mobile ions. It ionizes in water. So therefore, if I have HCl, okay, in the presence of water, it's going to form H plus and Cl minus. I have mobile ions, or what I like to refer to as mobile charge. Weak acids, on the other hand, like acetic acid, H2CO3, H2C2O3, which is vinegar, or carbonic acid, the H2CO3, do not dissociate in water, or they dissociate minimally, not enough where they'd really conduct any type of electrical current. I also said that they tasted sour. Let's review some naming rules from acids. So first we have binary acids, which are made up of two elements. They're made up of hydrogen and one other element. So how do we name it? We name it using the prefix hydro, followed by whatever the nonmetal is, changing the ending to ic. So for example here, you have hydrochloric, you change the chloride to ic, acid. Hydrobromic acid, hydrosulfuric acid. Those are binary acids. Then you have what's called a ternary acid. A ternary acid is more than two different elements. These usually include a polyatomic. And I like to say that this sounds like a disease. Adic-itis. Meaning 8 goes to ic and ite goes to us. So let me elaborate on that. If the polyatomic ion in the acid ends in ate, ate, then we change the ending of the acid name to ic. So if you look at the acid here on the right, you have HNO3. NO3 is the nitrate ion. So we take the 8 on nitrate and we turn it to ic, and we make it nitric acid. Unlike HNO2, which is the nitrite ion, we change that to us. So nitrite becomes nitrous, and this is nitrous acid. So notice, even though all of these start with H, we're not saying hydro. We're not naming the H. The way that we know the H is being accounted for is by the end of the name, the acid. The word acid infers that it starts with H. And there's some other examples here. Here, chlorate goes to chloric, chlorite goes to chlorus, and here's an interesting one. HCN is cyanic. So it was cyanide, and that one changed to ic. Most of the acids that you incur or encounter on the Regents exam will be ones that you can find here in Table K. Common bases are found in Table I. Now, remember earlier we talked about an Arrhenius acid. An Arrhenius acid is an acid that has H plus as the only positive ion in solution. Well, we also have an Arrhenius base. And an Arrhenius base has hydroxide, or OH minus, as the only negative ion in solution. So when we look at table L, we see that the first three bases are hydroxides: sodium, potassium, and calcium hydroxide. These would all be considered Arrhenius bases because they all contain the hydroxide OH negative ion. Ammonia, on the other hand, NH3, could not be considered an Arrhenius base according to this definition. Arrhenius bases also conduct electricity. Why? Because when they dissociate in water, they form Na plus and OH minus. We have mobile ions. You will learn as we go through this unit that acids, bases, and salts are all considered electrolytes. Why? Because they all form mobile charge or mobile ions. Bases have a pH greater than 7, and just like we said with acids, the further you get away from 7, meaning the closer you get to 14, the stronger your base is. Each increase, again, of 1 pH is a 10-fold increase in base strength. So a base with a pH of 10 is 10 times more basic than one with a pH of 9. But we don't usually talk about bases according to strength. We always talk about hydronium ion concentration. And hydronium ion concentration is that H3O. We always measure pH as a measure of the hydrogen ion concentration. So before I said when we went from a pH of 5 to a pH of 3, that was a 100-fold increase in hydronium. If I go from a pH of 8 to a pH of 10, that is a 100-fold decrease in hydronium. So we always measure pH as a measure of hydronium or H concentration. Basic solutions conduct electricity. Mobile ions, they taste bitter. And bases can be formed when group 1 or group 2 metals react with water. So here you see Na plus water and it forms NaOH. The best way to remember that you have a base is it is going to be a metal plus OH. Okay? If you see CH3OH, okay, this is not a base. Don't be fooled by the OH. This is actually an alcohol. We didn't learn it yet, but we will. So you want to look for a metal and OH, and then you know you have a base. And you're going to learn in the organic chemistry unit that bases hydrolyze fats and turn them into soap through the process of saponification. And that's basically all you have to know when we get to the organic unit regarding soap making, is that saponification is the making of soap. And I always say that if you put a little O in between the A and the S, it would spell soap. So if I have 2 glasses of clear liquid in front of me, how do I know if the solution is water or it's an acid or a base? Well, I certainly don't want to taste it. We can use what's called a pH probe, which is a metal probe that detects electrical conductivity. Or we can use what's more practical, common acid-base indicators. An indicator is something that changes color in the presence of a solution. So let me explain how the acid-base table works. So if I have methyl orange in a solution and it turns red, it means it's an acid. So 3.2 or less, it will be red and it means it's an acid. 4.4 or greater, it will be yellow. However, it could still be an acid in this case because we know acids are less than 7. And if it's orange, which is a blend of red and yellow, that means it would be in the middle range, greater than 3.2 or less than 4.4. So let's do some examples over here. A solution yields the following test results with various indicators. Methyl orange, it's yellow. So we know it has to be greater than 4.4. Phenolphthalein, it's colorless. So if we look at phenolphthalein, colorless is less than 8.2. Bromcressyl green is blue. So if we look at Bromcressyl green, so it's got to be greater than 5.4. And thymol blue, it is yellow, which means that it has to be less than 8.0. So therefore the pH can be what? Well, thymol blue, it's got to be less than 8, right? And it's got to be greater than 5.4. Those narrowed the ranges down, the Bromcressyl green and the thymol blue. Therefore, your answer has to be B, 6.5. If we go down to the bottom, that's what it was. You can read through all the choices. Okay, that's lesson 1, and now you can do the practice work.